Hi, my name is Elahe Sultanagay from Carnegie Mellon University, and today I'm presenting our paper on developing an ultra-low power Wi-Fi tag that works with existing Wi-Fi infrastructure. In a smart world, there are many things that we want to find that are not power, like a bottle of pill or a package in a warehouse. RFID is specifically a technology developed for tracking and identifying objects. There's a battery-free tag like a barcode that attaches to the objects. It receives the signal from the reader and reflects back a modulated version of it. Since there is no active radio at the tag, it's well suited for low power applications. However, because of the deployment complexities, we don't really have RFID readers in every building. So we asked, what if we design a tag that can be detected and localized with any Wi-Fi connected device? So nowadays we have free Wi-Fi almost in any building, like homes, restaurants, hotel rooms. So you can imagine having these tags attached to your wallet, keychain, toys, or tools, and then you can just use the Wi-Fi in the building and your personal Wi-Fi devices like phone or tablets to find them. However, the main challenge is that the tag reflection is multiple times weaker than the line of sight or other multipath reflections, causing a high dynamic range. So the tag reflection could be very well below the noise floor. This is problematic specifically in Wi-Fi setups where we have separate Wi-Fi transmitter and receiver and no time synchronization between them. Other papers on Wi-Fi backscattering solve this problem by designing a tag that reflects a frequency shifted version of the received signal, so it won't interfere with other multipath signals. But this requires the Wi-Fi transmitter and receiver to operate in different wireless channels. But that's not how Wi-Fi networks work. The whole idea here is to piggyback tag detection on top of ongoing Wi-Fi packets. Here we present TagFi, an ultra-low power tag that is compatible with existing Wi-Fi infrastructure. And the main question we're trying to answer here are first, how can we backscatter ambient Wi-Fi traffic without modifying the normal operation of Wi-Fi networks, for which we propose an asynchronous tag reader architecture. Second, how we can overcome the dynamic range problem and separate the tag reflection from other multipath signals. We present a code optimized super resolution algorithm to address this. And finally, how to locate the tag from a single receiver like your phone or tablet, for which we leverage multipath reflections. So first, let's start with our proposed fully asynchronous tag reader architecture. We separate the source of power at the tag from the backscatter signal we use for tag detection. So we design a tag that is as simple and low power as possible, that it can be constantly on and modulate any received signal. Then the Wi-Fi devices do their normal communication and the tag independently modulates the reflection from it. The receiver then captures the signal measurements in the physical layer, known as channel state information, and searches for the tag reflection. So all we need at the tag is an RF switch and a Wi-Fi antenna. When the switch is off, the received signal will be absorbed by the load attached to the antenna, but when the switch is on, the antenna will be shorted, so all the received signals will reflect back. And that's how this tag communicates with the reader, sending 0, 1 bits by switching on and off. But how can we now separate the tag reflection from other multipath signals? To answer this question, let's start with an analogy that explains the high-level intuition. Imagine you're out in a dark night and all you can see is some weak lights in distance that you may not even notice. However, if one of these lights start blinking, even though the light is so weak, it gets your attention. And if it blinks with a unique pattern, you can even detect where it comes from. That's basically the intuition we are using to detect a very specific reflection from the tag in a signal processing pipeline. So the blinking in the previous example is basically the modulation of the tag reflection across packets. But pay attention that because of the asynchronous architecture we talked about earlier, we don't really know when the tag is switching on and off. So to extract the tag reflection, we use super resolution algorithms that take measurements of the mixed signal from multiple packets, combine them together, and then estimate the parameters of all multipath signals, including the tag reflection, such as their angle of arrival, angle of departure, and time of flight. But why just combining multiple packets in a super resolution algorithm is sufficient to detect the tag without having any notion of when the tag is switching on and off? The key intuition is that a modulated path is incoherent with other wireless paths, and by incoherent, I mean there is no constant phase and amplitude relationship between the two signals. But why is this true? So to explain this, I consider a system of equations only for two paths and for angle of arrival estimates, but it can be generalized to angle of departure, time of flight, or more number of paths. So let's assume we have the first packet, only the switch is off, so we only have the line of sight path, and the phase shift across the antennas is only caused by the angle of arrival of that path. During the second packet, the switch is on and we're going to have the phase shift resulted from both of these paths across the antennas. These two sets of equations can be written as a linear combination of the same variables. Here is angle of arrivals that we want to estimate, but with linearly independent complex gains. So this makes these two sets of equations independent, increases the rank of matrices, and brings the tag reflection above the noise floor. So here's, for example, an output of the super resolution algorithm in a case where the tag is on all the time versus when the tag is modulating. And you can see how this incoherent relationship of line of sight and modulated tag reflection helps to easily detect the tag reflection. Okay, so far we were able to estimate the parameters of multipath signals, including the tag reflection. But how can we detect which one is actually coming from the tag? Here's the interesting part that once again the tag modulation comes to play. So from all the resolved multipath signals, the tag reflection is the only one that is modulated across Wi-Fi packets, and it is only detectable when the packets are combined in the super resolution algorithm. So we have the paths estimated from combining multiple packets. We then applied the same multipath resolution algorithm to on individual packets. A candidate tag reflection is a path that is resolved from packet concatenations, but not the individual packets. In the interest of time, I don't go to the details here, but please refer to our paper if you're interested to learn more about how we differentiate the tag reflection from static and mobile paths using some clustering and correlation techniques. So by the end of the tag discovery phase, we have the angle of arrival and angle of departure and time of flight parameters of the tag. Now let's see how we can locate the tag from a single receiver. To locate the tag, all we need is the direction and the length of the reflection path from the tag and the line of sight between the two Wi-Fi devices. So we can form a triangle in this space and solve it for the tag location. So here, instead of using multiple receivers for triangulation, we are using the multipath reflection from the tag to form this triangle. Here's the end-to-end TagFi pipeline for detecting, identifying, and localizing Wi-Fi tags from a single Wi-Fi receiver. We implemented multiple prototypes of TagFi by using off-the-shelf components as we saw earlier. We also have integrated PCB prototypes of the tag with a custom designed patch antenna. So just to emphasize, the tag here doesn't have an active radio. It's just an antenna connected to an RF switch. We develop a localization system on top of it, and we only need a personal Wi-Fi device paired with an access point in the building. Here you can see the power consumption profile of our custom design tag. Both the MCU and the RF switch have extremely low static power consumption, so the tag only draws significant power when the MCU has to wake up, process the next state, and change the state of the RF switch. So the overall power consumption of the tag is dependent on the switching rate. For example, on a switching rate of 100 Hertz, the power consumption is as low as 11 microwatt, which could operate on a 3-volt lithium battery coin for 5 years, or you could use any other energy harvesting approach. We evaluated these systems in the lab and a large arena. We placed the Wi-Fi transceivers and the tag in different locations and tested it for over 100 different scenarios. As you can see in this figure, we can achieve a median accuracy of about 30 centimeters to locate these tags in the 2D space. Also, the working range of TagFi starts from 100% detection when the tag is in 1 meter away from the transceivers and degrades to 50% at 8 meters, which is still sufficient for a home or office setup. We also developed an augmented reality interface that collects the Wi-Fi signals and locate any number of active tags and shows it to the user with an AR overlay. Here's another setup with multiple tags. As you can see in this video, we can detect and localize all of the active tags at the same time. The key point here is that each of these tags have a different modulation rate, like how fast they are switching on and off, and that's what we're using to detect and differentiate all of them. So there are still many opportunities to improve TagFi. One is the operating range that is, as I said, still limited to 6 to 8 meters. This may be good enough for homes or office setups, but may not be sufficient, for example, for asset tracking in warehouses. But TagFi can naturally benefit from some of the recent advances in Wi-Fi technologies like massive MIMO or millimeter wave frequency with directional communications, and that way we can improve the accuracy and range further. The good point is that the TagFi architecture is fully compatible with these Wi-Fi technologies. Another avenue for improvement is extending TagFi to 3D localization, for which we either need multiple receivers or planar antenna arrays at the receiver. And finally, extending TagFi for high mobility scenarios where we can leverage tracking methods like temporal measurements and Kalman filter. So to summarize, TagFi is an ultra-low power Wi-Fi tag that is compatible with the Wi-Fi networks in any building. To find the objects, we can use any Wi-Fi link in the building, and such an approach can evolve wireless medium into an intelligent sensing platform in more environments.